All right, so our last talk for the day is Tim Miller from University of Waterloo, telling us about vertex models for the product of our permuted basement Demazure atom times a Schur polynomial. Please take it away, Tim.
All right, okay. Thank you. I guess today I'm going to be talking about all these words that you see on the title. Um, so first, I'll just go through some notation. So throughout all of every time you see a list, a permutation, a partition, a set of variables, they all have to have length n just for all the statements to be correct. Lambda mu nu will always be partitions. The only tricky thing is we might allow them to have size 0. Everything else is pretty standard. ID is the identity permutation. W naught is the permutation that reverses everything. And so we're going to be talking about a structure coefficient problem, which is a classical problem in algebraic combinatorics. The most classic example is the Littlewood-Richardson coefficients, C lambda mu nu, that you get when you expand the product of two Schur polynomials. And today we're going to be talking about the product of a permuted-basement Demazure atom and a Schur polynomial, and these coefficients A, alpha, lambda, beta, sigma. So Alexanderson and Sani show that these coefficients are non-negative integers and express interest in the combinatorial rule, which is what we now have. First I'll just explain what these polynomials are connected to. So 2008, Haglund, Heyman, and Lohr gave this combinatorial construction for non-symmetric Macdonald polynomials in terms of these tableaux called skyline tableau, and they basically look like this. And on the bottom, you have a permutation, and if you just those red values are called the basement values. And if you just permute the basement, then you get the so-called permuted basement non-symmetric Macdonald polynomials. And if you let the sigma be W naught, you get the standard non-symmetric Macdonald polynomials. If you let Q and T equal 0, you get our polynomials that we're interested in, permuted basement Demazure atoms. Or if from there you let sigma be W naught, you will get the so-called Demazure characters. If you let be that identity, you get Demazure atoms. And if you, from a Demazure character, if you let the weak composition be a partition, you get Schur polynomials. So Haglund, Luoto, Mason, and van Willigenburg give expansions for characters, timeshares, and atoms timeshares in terms of skyline tableau. But we have a more general formula now in terms of vertex models, which we'll get to in a bit. But first, I'll give an example. So here is a skyline tableau on alpha and sigma. Alpha tells you how tall the columns are in the tableau, and sigma just tells you what to put in the basement. And you want to fill with positive integers where there are no descents. So every time you have A over B in a column, A must be less than or equal to B. And then there are some tricky conditions on triples, which I don't want to put too much time into, but basically there are these two types of triples. And if you have uh, the left column greater than or equal to the right column, and you see this configuration, then that's a type A triple, and then similar for a type B triple. And basically, the only condition that you need to satisfy is that B cannot be strictly between the values A and C. And here's an example of the two tableau in our case. Then every tableau is assigned weight that just counts the number of blue entries in the tableau, essentially, and then you sum over all weights. and that gets you our permuted basement Demazure atoms. And so in 2003 and 2004, Newton, Tao, and Woodward developed puzzles to calculate Littlewood Richardson coefficients. You basically have an equilateral triangle where you encode partitions on all three sides, and then you fill in all possible ways with these puzzle pieces, which are allowed to be rotated but not reflected. And the theorem is that Littlewood Richardson coefficients are the number of ways that you can fill in these puzzles with these boundaries. And in 2009, Paul Zinn-Justin just sort of drew a slightly different image, which is exactly the same thing. But he came up with these by sort of envisioning everything as a particle model. And he had very cool proof that these things count the Littlewood-Richardson coefficients, which involved basically taking three different types of particle models and gluing them all together, and that put Schur polynomials and puzzles all in like one big combinatorial picture. And that's the style of proof that we'll use today. So what's a vertex model? Vertex models are a tool from statistical mechanics. They're used to model particle systems. In algebraic combinatorics, they can be used to find Cauchy identities or branching formulas or structure coefficients. A classical example is the six-vertex or square ice model. So in the six-vertex model, there are six types of vertices, and you can think of them as being configurations of a water molecule, and where we just say that these two edges can't connect. And then it's called the square ice model because you just imagine you have a two-dimensional square of ice and you fix the boundary, and then you would fill the interior in all possible ways. And then every vertex is given a weight. In this case, let's just say everything has weight 1, in which case what the model will do is it will just count the number of ways of filling in the square of ice. And that is the number of microstates, which is used in the calculation of entropy. But then you can give all kinds of different weights to vertices in the six-vertex model. For example, we can get the Schur polynomials. And we're going to draw them like this. These vertices, if you impose those rules that we had before, they're just in bijection with these tiles, where we want to glue them together so that blue lines match along edges. And we'll give them these weights. The first four are all 1. And the fifth one gets this weight of xc if the tile occurs in a column C, which we'll see below. And the last one is actually just set to 0, so it doesn't exist in the model. So sometimes these are called 5-vertex models because of that. And so to compute the Schur polynomial on 33110 with our model, first you enclose the partition 3310. You take its Young diagram. And then you start at the bottom, and every time you move vertically up, you put a blue dot. Every time you move horizontally across, you put a white circle. And then we read lambda, we read this sequence of dots, and what that will do is encode lambda. We put that on the side of this grid, and then on the bottom, we put all blue dots. And each column is assigned the variable xc, where c is the column number. We fill in all possible ways. And then, so for example, this filling will have this weight because there are two shaded squares in column one, so it has x1 squared, two shaded in column two, so it is x2 squared, and so on. And these are also straightforwardly in bijection with a semi-standard Young tableau. So the way you get it is you just read the line. So x5, so the line starting in column 5 tells you how to fill in the top, and then uh, so on. Bam, bam, bam. And then you just sum over all of them to compute the Schur polynomial. And then I read this paper from Borodin and Wheeler in order to think about Demazure atoms initially, but it actually tells you how to deal with permuted-basement, non-symmetric Macdonald polynomials in full generality, so you can set Q and T equal to 0 and get our permuted-basement Demazure atoms. And basically, they have a vertex model that looks like this, where the lines are allowed to move. So only one line is allowed to move vertically within a column, but multiple lines can move horizontally within a row. And if you draw it this way so that the lines sort of stay in their lanes, then I haven't explained all the details of this model because we're not going to spend too much time on it, but there's this nice rule, which is that these lines, as long as you ensure that they only cross once, it computes the polynomials we care about. But I took that picture and I sort of made it compatible with the Schur polynomial model. And so those pictures will look like this. There's a very similar model as well from Brubaker, Buchimas, Bump, and Gustafsson, just for Demazure atoms without the permutation. So all of this so far is not very new. But here's the model. First you take these tiles, and now we label them with numbers. And it's pretty straightforward. It's just with these tiles, you must always have that I is less than or equal to j. And with these tiles, you have to have that sigma L is less than sigma k in order for that crossing to happen. And so here's our example. We encode weak compositions in a similar way to the way that we encoded partitions before. What you do is you take the parts in the weak composition, and then you sort them. So in this case, you would get this partition 2, 2, 1, 0. And then you label the verticals with numbers that indicate the index of the part of that size. So what I'm saying is, okay, the first part has size 1, and so we label that 1. Now the second part has size 0, so the 2 goes at the bottom. And then the last two parts both have size 2, and so we put 3 and 4 on these rows, but there are multiple ways you can order them. So you always order them so that they're increasing when you go from top to bottom. And then you read off alpha from these sites, and you put that on the side of a grid, similar to as we did before. And this time we put sigma inverse on the bottom. And that's just to make it match with the standard definition of the atoms. And you fill in all possible ways. You get a weight just as before. And just to put this in bijection with the skyline tableau, what you do is line number 1 tells you how to fill in column number 1. And then line number 2 tells you how to fill in column 2, and 3, and 4, And yeah, that's a bijection. Oh, and then we have some new, oh, I'm really running out of time. Okay. All right. So now, all right, here's the theorem. All right. We have some new tiles and here they are. They all have weight one, and we fill in this diamond piece uh, with with these boundaries. Here, lambda tells you how to fill in a partition. You fill in all possible ways, and that will calculate our coefficients that we care about. And that's almost true, except you have to have this extra condition on adjacent diamonds. I must always be less than j when you do this. And I'll just do an example. These are some two possible fillings. I think I'm going to skip this part. It's basically that sigma tells you whether or not you can actually do this legally, whether one can actually legally cross three or not. So those are two possible fillings. And then the best part of this is the proof. So the proof is we need a whole bunch more tiles. And then what is true is that these two columns are equivalent. They'll have equivalent weight as long as you let R and U be white or red. And so here's some examples. Left-hand side equals right-hand side. They both have weight XC, but like more interesting things can happen. These two will cancel. You have XC squared and negative XC squared. And that will equal 0 and there's no way to fill in the right-hand side. And then the main idea of the proof is that you just start with this configuration, and then we can apply our column lemma and flip this, and then flip that, and then flip that, and then flip this. Right. And then, okay, so what that shows is that these two things are equivalent. And then there are only 3 steps to the proof. So the second step to the proof is you just examine the left-hand side, and this is always fixed, and so it disappears. We can get rid of that, and then this thing can break up into a Schur polynomial times an atom, and so this whole thing just manifestly is an atom times a Schur. I'll leave that for a few more seconds. And then proof step 3. On the right-hand side, this part will always be fixed. And so we can delete it. And then we have this, and then we can split that up. And then on the interior, we always have this beta encoded, but it's a variable weak composition beta. And so you have to sum over all possible betas. And then this thing is the atom on beta. And so we get this summation where our coefficients are counted by these diamonds.
18 minutes.
Okay. And well, that's the proof. In a nutshell. And yeah, that's basically it. I was just going to maybe talk more about the Yang-Baxter equation. So like vertex models are constructed from these R matrices, which you can basically think of the tiles as telling you how these R matrices work. And basically this R matrix tells us that these two edges map to these two edges with some weights, and like similar for like these tiles tell us something else. Those map to those. And then like our vertex models usually satisfy the Yang-Baxter equation, which is morally this, but I should probably put some parameters in there. In previous results, this translates to like this cube rule for any boundary. But we have this like more complicated rule, and I would really like a cube rule, but I can't figure it out. But maybe this is the only thing that's really possible. Anyways, that's all I have for now. Thank you very much.
All right, well, thank you very much. Thank you very much for a beautiful talk. So maybe we have time for 2 quick questions, and then I'm gonna open so we can have questions for all the speakers after that.
Okay.